talk about finite Galois extensions. So recall we have proved Artin's theorem, and these are all now some nice consequences. So here's a theorem which characterizes finite extensions which are Galois. So let K over F be a finite extension. Then K over F is a Galois extension. If and only if the following degree criterion holds, that the cardinality of the degree of the extension Kf is the same as the cardinality of the group of F automorphisms of K. Okay. So let's prove this. So recall what the group of F automorphisms was. So aut K over F just meant take all automorphisms of K which are identity on F, right? And this of course appeared in our, so let me just call this group gamma. So this appeared in our earlier characterization of general Galois extensions. Recall that an extension is Galois if and only if the fixed field of this group of automorphisms is the base field itself. Okay, so we'll come to that the course of the proof. So I have called this as gamma. So the first observation is that observe the finiteness of this extension implies the finiteness of this group. Okay, so why is this true? Well, what does a finite extension look like? So here's one way of thinking about a finite extension. I start with the base field. If there is at least one element outside the base field which belongs to my field K, then what I do is I adjoin that element. So if I can find one element in K which is not in F, I adjoin it. I get an intermediate field F of alpha 1, right? If F alpha 1 is still not everything, there is something more, then I can adjoin one further element. I pick an element outside and adjoin it, and so on. So I keep going. Now at every step, the extension that I have created has degree at least 2, right? The degree of this extension is at least 2 because I have chosen alpha 1 that doesn't lie inside F. Okay, so at every step I have at least a degree 2 extension, and the overall extension is finite, right? Which means that I can't keep going on and on like this forever, because recall that the degrees are multiplicative, right? So Kf is just the degree of the product of the degrees of all the intermediate extensions. So therefore this process has to stop. So this means that in particular K is just obtained from F by finitely many adjunctions. So this has to look like alpha 1, alpha 2, alpha s, okay, for some finite value s. Could be 0 even if K and F are equal. Okay, so in other words there are no alpha s's if K and F are equal. Okay, so what does that mean? So if I can obtain K from F by finitely many adjunctions, then the effect of an automorphism. So observe now that sigma from K to K. So if sigma is an automorphism of K over F, this sigma is uniquely determined once I tell you what it does to the alpha i's. So sigma is uniquely determined by the values of sigma, by the values sigma evaluated on these generators. Okay, why is that? Well, because sigma, recall sigma on F is already the identity. I know how to evaluate sigma on elements of F, and then on other elements, once I know the value on sigma alpha 1, this determines sigma uniquely on the first extension, right? So I just argue extension by extension. I know the value on F, it's the identity, and I know the value on the generator alpha 1, so that uniquely determines the value of sigma on F alpha 1. Okay, so that's like a sort of an easy exercise. And since I know the value on f alpha 1, then I adjoin just one more element, and the value on of sigma on alpha 2 together with its value on the field f alpha 1 will will tell me how to define, will uniquely determine sigma on f alpha on alpha 2. Okay, and so on. So I just go extension by extension, and so the value, what it does is it determines sigma uniquely on k. Okay, all values on k are uniquely determined by just knowing the values on the generators. But observe that the possible candidate values for the generators are only finitely many. Okay, in other words, so observe or recall the following fact. If I had an element alpha in this extension k over f, then and let m alpha denote its m alpha of x in fx be its minimal polynomial. So this is the minimal irreducible polynomial satisfied by alpha with coefficients in f. Then so then observe for all sigma, which is an automorphism of k which fixes f, sigma of alpha is also a root of the same minimal polynomial. Sigma of alpha is a root of m alpha of x. Okay, so this argument has occurred many times before, that if alpha is the root of some polynomial, then sigma of alpha is also the root of the same polynomial, okay, over the base field, because sigma fixes the coefficients from the base field. Okay, so given this, what does it imply? In particular, m alpha of x only can have finitely many roots in k. This means that sigma of alpha is only one of finitely many possibilities. So this belongs to the set of roots of m alpha in k. Okay, so each sigma alpha I has finitely many choices. Okay, so sigma alpha 1, I can possibly map it to one of finitely many possibilities, right? So sigma alpha 2, similarly, there are only finitely many choices, and so on. So what does this mean? Finally, it means that so maybe I should say alpha 1 can map under sigma to only one of finitely many choices, and so on. So this finally implies that the possible values of sigma itself is only finitely many. Okay, so this in particular implies that the possible choices for elements sigma of gamma itself is only finitely many. Okay, so this is just the simple finiteness observation, that if the extension is finite, then the group of automorphisms which fix the base field is also necessarily a finite group. Okay, now that means that we can now apply Artin's theorem. Okay, so observe mod gamma is finite implies Artin's theorem applies. And what did Artin's theorem say? It said that if you take k and gamma was any finite, so what was the hypothesis here? Gamma needed to be any finite subgroup of the group of automorphisms of k. Okay, so in particular we have taken gamma to be odd kf, okay, and that's known to be finite in our case. And Artin's theorem says that if you look at k as an extension of k gamma, so then the theorem says that this extension has degree exactly equal to the cardinality of gamma. So this is exactly Artin's theorem. So this is the assertion of Artin's theorem. Okay, but in our case, gamma is something special. Gamma is actually the group odd kf. Okay, which means it's the set of all automorphisms of k which leave elements of f fixed pointwise. Okay, what does that mean? Well, that says that k gamma actually contains f. Right? So this means in particular that f, elements of f, certainly lie inside the fixed field of gamma. Right? That's how gamma is defined in this case. Okay, so that's our case. So what does this say? This says then that this extension has degree mod gamma according to Artin's theorem, So, well, what is it that we want to conclude? So, conclusion is that the full extension, the overall extension from K to F also has degree mod gamma if and only if the extension on the bottom K gamma F has degree 1, right? Because Artin's theorem already told you that the top bit has degree equal to mod gamma. Okay, so this is what we have concluded, but this last conclusion just says that K gamma is equal to F, right? A degree 1 extension is just the base field itself. Now, K gamma equals to F should be a familiar statement. So, recall this is exactly one of the characterizations of a Galois extension. Okay, that if I take the group gamma to be the automorphism group of K over F and I look at the fixed field of that group of automorphisms, then it should be exactly F. Okay, so this, recall from our earlier theorem on characterization of Galois extensions, says exactly that K over F is Galois. Okay, so that proves this rather nice characterization of finite Galois extensions. So, this is yet another characterization now purely in terms of the degree of the extension. It says that the extension degree must be the cardinality of the group of F automorphisms of K. Okay, now let us also write out another corollary sort of along the same lines of Artin's theorem. So, let me call this proposition. This proposition says the following: let K be any field and gamma a finite subgroup of the group of automorphisms. This is the same hypothesis as in Artin's theorem. Okay, then two statements. Number one, K over K gamma. Recall this is a finite extension because Artin's theorem tells you that it's the cardinality, the degree of the extension is the cardinality of gamma, but we want to claim more than that. This is a finite Galois extension. Okay, finite is already done by Artin, so we are just trying to prove the Galois bit now. And statement 2, the group of automorphisms of K which leave K gamma fixed is exactly gamma. Okay, so let us prove this. So let's give this a name. Let's call this fixed field as K gamma, and let's call this group of automorphisms as G. Okay, so we need to say something about F and G, this theorem, the two parts. So observe that with these definitions, what do we know? That firstly that F, so F is K gamma. So observe G is definitely more than gamma, right? So gamma is a sub of G. So observe gamma is actually a subgroup of G. Okay, why? Well, by definition, because let's see, if I take elements of gamma, then by definition they fix the elements of K gamma, right? More or less this is by definition. Okay, since elements of gamma certainly fix K gamma pointwise, that's how K gamma is defined. Okay, and what is G? G is saying take all automorphisms which fix elements of K gamma pointwise. Okay, so the original elements of gamma are certainly part of this. So gamma is definitely a subgroup of G, but what does that imply in particular? It says that the fixed field of gamma, so gamma is smaller than G, so the elements of K which are fixed by gamma is definitely a superset of the elements of G, elements of K which are fixed by G. Okay, so when I have a larger group, it fixes fewer elements in general, right? So I know this K gamma contains Kg, but here's something that we know. What is G? G is just the space of all automorphisms of K which fix F, right? So I remember F is the same as K gamma for me. So this just says that elements of G certainly fix F. So the fixed field of G certainly contains F in our case. Okay, but so what's on the left and what's on the other end are actually the same. This is also F and that's also F. So we conclude from this that the fixed field of this potentially larger group G is actually the same as the fixed field of the smaller group gamma. Okay, so this is the first conclusion, and further this statement here that Kg is actually equal to F. What does this say? Just like we did in the previous part, this just says that the fixed field. So what is G? G is exactly the group of automorphisms of K over F, and if the fixed field of this group is F, this exactly means that K over F is Galois. This is the equivalent characterization. So this is our previous theorem characterization of Galoisness or Galois extensions in terms of the fixed fields. Okay, so that's proved the first part because finite we already knew. Okay, so now let's do the second part. We need to check that the automorphism group is exactly gamma. Okay, so what do we know to prove the second part? So we therefore know, so because we have just shown it's Galois, so by our previous theorem that we just did, which characterizes finite Galois extensions, we know the following, that the degree of the extension must be equal to the cardinality of the Galois group. Okay, so this is cardinality of aught K over F. Okay, but well, recall K over F on the other hand is K over K gamma. That's how F was defined, and this by Artin's theorem, K over K gamma is mod gamma by Artin's theorem. So what does this say? Well, it says G and gamma have the same cardinality and G contains gamma to begin with, right? Where is that? Gamma subset of G. So this means that gamma is a sub of G and they have the same cardinality, means they must be equal to each other. Okay, so the key point here is really the following, that we a priori potentially have a larger group G. Okay, it could be bigger than gamma, but the fixed fields are the same. Okay, that's what we are able to prove from this. And the fact that they have the same fixed field then also implies in this case that the groups themselves are the same. Okay, so all of these arguments, so this is sort of maybe a small argument split out of this broader thing of Galois theory. We will soon see that this forms part of what's called the fundamental theorem of Galois theory. Okay, so that's going to be what we'll do next.